question. So you're not going to get feedback immediately on that question until you finish your exam and send it in, which actually is kind of a good thing. If you were getting, in a wrong road, you told the screws from the test. So.
But then after you send it in, it
you
tells
get
you
your
what you
results
got wrong?
immediately. Yeah, you can see what you got. You see your score, what you got right, what you got wrong. You can go back and review it, you get a solution and all that. Yeah, and you can also review it outside the testing center. When you go to results, you can go through and look at your test and see your answer, the right answer, work out solutions, all that.
The practice exam, is that pretty much the same type of questions that's going to be on the actual exam, or is it not?
Okay, let me answer that carefully. The practice exam, the way I created the practice exam is the tests are algorithmic, right? That means that the questions you get and the numbers within those questions are created by the software. I don't create them. I set a probability for each question, and then the software picks the question for you. So that's different, right? Different mix of questions, different numbers within those questions. The way I created the practice exam was I created exam 1, put a password on it that only the proctors are supposed to have. And then I copied it and said practice exam and took the password off. So when you take the practice exam, you are taking exactly the same type of exam that you'll take in there. Of course, the mix of questions will be different on every time you bring up the test, and the numbers of those questions will be different. But it's going to look exactly the same. Yeah, so the practice exam is a real good idea of what to expect.
You gave notes in class. Should we study those notes, or should we only, if we studied only, the little questions that it gives us on finance lab? Which ones will be on there, or will both be on there?
Okay, so the homework questions are your test bank. The only questions I can ask on an exam are in your homework. So if you've mastered all the homework problems, there'll be no surprises on the exam. Exactly the same questions, same wordings and everything, just new numbers inside. So the notes are just to help you get through the homework questions. The homework questions are how you prepare for the test.
So how many questions from each chapter?
All right, so you got 3 chapters on exam 1, chapter 3, 4, and 5. 25 questions, so the breakdown is 8 questions from chapter 3, and 8 questions from chapter 4, and 9 questions from chapter 5.
Wednesday and Thursday we have to set up a time to go take it, is that what you said?
Wednesday it's not open. We don't have anybody available to proctor it. Thursday I'm going to be in there. Instead of having class in here in office hours, I'll be in the testing center from 10:30 to 2:30. You guys can show up and take a test. You don't have to make an appointment or anything like that. I'll be in there proctoring on Thursday.
And it closes at 5 today.
Is that right? What time did I send out?
I think it's almost at 6.
6.
I think it's 6. But yeah.
So we better take it today, it sounds like.
If you're going to get, well, we've got plenty of computers. So there's about 80 of y'all in the class, and there's like 85 computers. So everybody shows up at once. It's not a problem. But if you want to take it multiple times, I try and get plenty. Yes. Yeah, absolutely. Absolutely. You can take it all 3 times on Thursday if you want. That's fine. Beware of the time limitation. You've got 100 minutes once the exam is open. Bless you. And at 2:30, I've got meetings after that, so I've got to go. And I won't have eaten or gone to the bathroom in like 5 hours. Right? So at 2:30, I'm out of there. So if you're planning on taking exams multiple times, show up at 10:30. Make sure you got time to get them done. 2:30 rolls around, shut the lab down, I'm out. And the same is true for the proctors. They're even busier than I am down there when it rolls 6 o'clock rolls around.
How long does it take the average person to take it? I know, like, you gave 100 minutes, but how long does it take the average person?
Yeah, fair enough. So on average, I didn't look from last semester, but the previous average was right around like 80 minutes, 90 minutes. And those people take the full 100 minutes. What I can observe in that is, are they actually working that full 100 minutes, or are they using all that time for that machine? But the average actually submitted to put in. Oh yeah, you can go back and forth the whole time. Yeah. If you guys haven't yet, pop open the practice exam and check it out. Get a feel for what you're looking at. But it doesn't count towards your grade. You can look at it as many times as you want. Doesn't matter. All right. In fact, if you guys have read the study guide, I would strongly suggest sometime before you sit in there, sit down with nothing but your formula sheet, your calculator, a blank sheet of paper, open that practice exam and see how you do. Don't cheat yourself. Try and work it like a real test. You're going to have some holes in your knowledge you didn't know were there. There are going to be places you were relying on the example problem you didn't realize you were relying on find that out now before we sit as a real test, right? We have to go back and look at this.
In chapter 4, so how do we know like which one was to use? Because like on the homework, like I don't know, at times I didn't know which one to use until I looked at the example.
Okay, because you're going to have worked that problem so many times in a row that the moment you see the question stem, you know what formula to throw at it. That's it. Practice, that's it. It's repetition.
So there's no like reading the problem and knowing what it's asked like exactly to know what formula.
By the end of the class, you're going to be able to do that.
But now it's just
But right now, that repetition is how you get there. Yeah. You'll have most of these formulas memorized. Like, good questions. Anything else about the test? All right. Let's jump into chapter 5 then. So chapter 5 is titled Interest Rates in the Text. And that's where we're going to start. We're going to start by defining a couple of different terms for interest rates. There are 3 different definitions we're going to look at. And really all chapter 5 is going to do is introduce the idea of multiple compounding periods within 1 year. In chapter 3 and chapter 4, we had cash flows just happening on an annual basis, right? So we didn't have to be careful about what interest rate we were talking about. Once we get into looking at things with monthly payments, like your typical consumer loans, right? Or later on, we're going to look at bonds, which tend to pay semi-annually or twice per year. We have to start worrying about what interest rate are we talking about. Are we talking about the annual rate? And if we are talking about the annual rate, are we talking about the effective annual rate or the annual percentage rate that was defined by Congress? Right? Those 2 very different things. Or are we talking about the monthly effective rate on your credit card statement or your car loan, right? Those things are very different, and how we use them is different. Okay, so let's start by defining rates. Once we are comfortable with the different types of rates, we can jump right into the complex problems. Alright, so defining rates. Number 1, that little R that we've been using in all of the formulas, right? We've just been calling the interest rate R. Okay, that guy is the effective interest rate per period. Probably because the user is too rapid. Okay, the effective interest rate per period. Right? And that could be per year, which is what it was all through chapter 3 and 4. Could be per quarter. Per day. There, it could be anything. And the effective interest rate per period. So what rate are we actually earning? Or what rate are we actually paying within this period? All right, the rate we're most used to seeing in the U.S. is what's called the APR, the annual percentage rate. All right, the APR has a definition, a strict definition, where the APR is equal to R, that periodic effective rate, times N, where N is the number of compounding periods and is the number of compounding periods per year. the US, on any sort of consumer loan, the lender is required to report the annual percentage rate. Okay, so this is the rate that you see. You open up your credit card statement, it'll say APR, or your car note, or your mortgage if you have one, it'll show you the APR on there. Now, note what this does not do. They're taking in the case of a car loan, you're making monthly payments, right? They're taking the monthly effective rate, that little R, and multiplying it times 12, the number of compounding periods per year. What that is not doing is taking account of the effect of compound interest, right? Because every period you pay a little bit of interest, and then that interest gets locked into your balance in the next period, and it compounds over time. So this rate, the APR, does not include the effects of compounding. And so it is understated if there is more than one compounding period per year. So when you look at your credit card statement, it says your APR is 12.24%. Right? That's not your actual effective rate. That is excluding the effects of compound. All right, while we're on APR, it's also worth noting if we take this definition of APR, we can rearrange this thing and solve for the periodic effective rate if we're given the APR and the number of compounding periods per year, which is often what's going to happen when you look at a consumer loan, right? You want to find out what the effective rate per period is. They give you the APR and the number of compounding periods per year. All right, so let's rearrange this thing to solve for R. We're just going to divide APR by N. So our periodic effective rate is defined as the APR divided by the number of compounding periods per year. All right, there's another definition of interest rates, goes by the funny name EAR. We usually say EAR instead of year. That is your effective annual rate. Okay, and this thing is exactly what the name sounds like. It's your effective annual rate. It's your annual rate of return, including the effects of compounding. It also has a formula definition and how it relates to the periodic effective rate and the annual percentage rate. Okay, so the annual effective rate, or the effective annual rate, is equal to 1 plus APR divided by N, raised to the n minus 1. Well, all of those terms retain their prior definitions. So the APR is the annual percentage rate. The n is the number of compounding periods per year. Okay, and we want to note two things about this. First, APRs on the right-hand side here, we can't turn around and solve this thing for APR if we're given the effective annual rate. The other thing that we'll end up using a few times is notice inside the parentheses here, this term APR divided by n. Right, we've already seen that that is something else, right, that carries another name. That's our little r, that's our periodic effective rate. So we can rewrite this formula, which they do a time or two in the homework, and just don't show you that that's what they're doing. This way right here by making a substitution. Right, so in some cases you're given the periodic effective rate, you don't have to calculate it, and you're asked for the effective annual rate. You just plug it right in.
Do we get to drop the n on the bottom?
They're exactly the same thing. There is no difference between these two formulas.
So we don't have to put the n on the bottom like that.
It depends on what you're given. If you're given the periodic effective rate, this thing right here, then you don't need to. You're taking an extra step if you plug in and do APR over n. You can't. You get the right answer. But if you're given R directly, you can just plug it in. Okay, right? So R is equal to APR over m. This is APR over m, so I just substituted n on. All right, if you needed to rearrange this thing and solve for APR and just play some algebra games, and these are actually all on your formula sheet and used to have them on there. But just rearranging the EAR formula and solving for APR, you end up with this guy. Which one you use just depends on what information you're given and what you're asked to give back. And none of these are formulas you have to memorize. You have all of them right here, right in the chapter 5 section here on the formula sheet. All right, so we okay with the difference between those three rates, the R, the EAR, and the APR? What's the difference between the APR and the EAR? Compound interest is within the effective annual rate and not the APR. Right? We'll throw this down too. If there's only one compounding period per year, like there was in chapter 3 and 4, then the periodic effective rate is equal to the APR because n is 1. And also because n is 1, the APR is equal to the effective annual rate. All three are the exact same thing. There's no need to distinguish between them. They're all the exact same. More than one compounding period per year, and the relationship looks like this. The effective annual rate is greater than the annual percentage rate, which is greater than the periodic rate. relationship is worth keeping in mind as you're looking at consumer loans. You try and decide how to borrow. Know that that annual percentage rate, unless you're making payments only once per year, it's always understating your true borrowing cost. Always. Okay, sample problems then? Y'all look like you're ready to have fun. That's good. Oh, sorry, sorry. That one's really simple. Which one's more interesting? Yeah, let's do number 2. We can do number 1. This one's more interesting though. Okay, and maybe more relevant to all of us. You're considering 2 ways of financing a spring break vacation. You could put it on your credit card at 14% APR, compounded monthly, or you could borrow the money from your parents. We want an interest payment of 8% every 6 months, which is the lower rate. Alright, so we need to come up with a way to compare these. It's tempting to just look at the number and say, oh, 14% sucks compared to 18%. Right? But they're 2 very different numbers. The 14% is the annual percentage rate, which we already know is not the effective annual rate. We're going to deal with that. The other rate, it says they want 8% every 6 months. So they've given you the 6-month effective rate, right? Just the simple interest rate every 6 months. Those are 2 totally different rates, and they're not apples to apples. We can't compare them. So we need to put them both in the same terms. And the problem is going to give us a hint how to do that. It's going to say the effective annual rate for your credit card is 20%. So it wants us to convert that APR to an EAR. Alright, so we've got the EAR formula, which is equal to 1 plus the APR divided by M raised to the M minus 1. Right, and this ought to look, I didn't mention this before, this formula ought to look awfully familiar. It looks an awful lot like the future value formula, right? It's doing the exact same thing. It's compounding that interest rate for us, just like a compounded future value. Alright, so for the credit card, the relevant numbers on my problem are 14% APR, so 0.14 as a decimal, divided by N, the number of compounding periods per year. Okay, it tells me in the problem that it's 14% APR compounded monthly. Right? 12 months in a year, so there are 12 compounding periods per year on the credit card. Alright, so plugging that in. We want to be really careful with the order of operations here. You can type it in exactly as you have it written. You can work it in chunks, however you're comfortable doing it. Use the VA2 plus. We'll just type it in like it's written. So open parentheses, 1 plus 12, close parentheses. And it does the division first and the addition like it's supposed to. And then y to the x, 12 raised to 12 power equals and 2 decimal places, so we're good there. make sure we put everything in right. We're expecting, since there's more than one compounding period per year, the effective annual rate should be higher than the stated APR, and that's the relationship we're seeing, so that's good. 14.3%, excellent. Okay, so you guys are punching buttons and following along. Coming up with those numbers, okay? We good? Alright. The second part then is, what is the effective annual rate from the loan for the loan from your parents? Okay, I'm going to use this same formula, the effective annual rate formula, but here I'm not given the APR. I'm given the periodic effective rate, 6 or 8% every 6 months. Right? So I can go ahead and turn that into an APR and plug into this formula, right? Or I can recognize that I'm given R is equal to 8%. Right? And know that APR divided by N in this formula is actually R. And I can just plug 8% right in. Oh, sorry, that should be raised to N there. All right, so N is the number of compounding periods per year. If it's 8% every 6 months, how many compounding periods per year do I have? I've got 2, right? 2 6-month periods in here. Awesome. So 1.08. Which is in the neighborhood of what I'd expect. If I just double it, if I just multiply it by 2, I get 16%, and I'm expecting something higher than 16%. So that smells right. Okay. All right, now which looks like the cheaper way to finance your spring break vacation? Credit card. At 15% is cheap. Relatively cheap. Right. So a good example of when to know when to substitute that in that R and when you've got to do the APR divided by number of compound periods. Any questions on this one? It's going to get way more interesting in a hurry. Not quite yet. All right, let's check out number 5. There are a couple ways to work this one. But it's not obvious what they're doing on the example solution, so I'll talk about it a little bit. All right, number 5 says a payday loan is structured to obscure the true interest rate you're paying. For example, in Washington, you pay a $30 quote fee for a $220 payday loan. When you repay the loan, you repay $250. So the $220 plus the $30 fee. What is the effective annual interest rate on this loan? All right, so let's map out your actual payments. All right, if you were to take out this loan, it's a $220 loan, so they would give you $220 today. Right? And what you would promise to repay is the $220 one period from now. In this case, it's 2 weeks. plus a $30 fee for a total of $250. And what it wants to know is the effective annual rate. So we're eventually going to use this formula. Because I've worked this problem a whole bunch of times, I've gotten comfortable with it, and I'm able to look for it a little bit and know that, I've got a 1-2 week period here. So when I solve for the rate, I'm going to have the periodic effective rate, right? I'm going to have that little r. So the actual variation of this formula I'm going to end up using is this. So there are two variables in that equation. There's r, the periodic effective rate, and there's n, the number of compounding periods per year. N is easy enough. The loan is for 2 weeks, and it tells us in the problem, assume 26 bi-weekly periods per year. Okay, so there's 26 of those 2-week periods in 1 year. So there's 26 compounding periods per year. N is given. What I don't have is r, periodic effective rate. And there are several ways that I can get it. I have essentially a present value and future value. I can plug into the present value, future value formula and solve for r, which is nothing more than a percentage change. So my future value is 250. The present value is 220 times 1 plus r. Here I'm only considering 1 period, right? The payment's only happening over 1 2-week period. So when I go to solve for r, I end up with 250 over 220 minus 1 r. An equivalent way to work this problem is to look at it from the lender's perspective. Okay, the lender gave up $220, and in exchange for giving that up, they're going to receive a $30 fee, right? They give up the $220, they get the $220 back 2 weeks later, but they receive the $30 fee. So from the lender's perspective, the cash flow they received was $30. What they had to give up to get that cash flow was $220. So what percentage of 30 is 220? That's their rate of return. Either one of these are going to give you the exact same answer, just different ways of looking at it. Store 1. Right, because we know that's worked out to 13 decimal places. We're going to turn around and plug it into this EAR formula, and I didn't want to introduce a rounding here. Okay, so I'm storing that guy in the 1 key, I think SEO1. Hey, I've got my periodic effective rate, so I'm ready to plug into the EAR formula. So 1 plus 1.1364 raised to the 26, because there are 26 compounding periods in a year. So that guy plus 1. Yes. so that's my decimal version. How do I turn that into a percentage? How many places do I move the decimal? $2,676.20%, the effective annual rate on that one. Definitely missed credit card rate. Okay, any questions on those? Jumping between effective annual rate and annual percentage rate? Okay. Be real comfortable with the definition of those interest rates before we go to the next step. Any questions? Now's the time. Okay then, before we start looking at a couple of more complex problems in Chapter 5, what I want to do is introduce the time value keys on your calculator. Okay, and what we're going to say about the time value keys applies if you're using the VA2 Plus, which is amazing once you get used to it. If you guys are anything like me, you'll go through 2 or 3 of them because you smash them to bits while you're studying for the test. But once you get used to them, they're fantastic. But what we're going to say applies equally to those, or if you're using the calculator within My Finance Lab as well. And they both work the same way. All right, so let's talk about, let's say VA2 Plus. What we're going to look at are the TVM keys, the time value of money keys. All right, and if you look at the calculator, that's this row of 5 keys on the 3rd row, the N, I, the Y, the TV, ENT, and FUD. Okay, let's start by defining those things and saying a little bit about them. All right, moving from left to right, the first key is the N key. This is exactly what you think it is. This is the number of periods, the N in most of your formulas. If you've got an annuity, it's the number of payments. Moving right, we've got the I over Y key. This is the effective interest rate per period. I over Y stands for interest rate per year, but we might not be working with years. So just the effective interest rate per period. The 3rd key, PD, is present value. Roughly familiar with that by this point. PNT is payment. And then finally, the 5th key, FD, is future value. All right, I know I've bored you guys to death up until this point, but key in right here. Wake up for just a second, because what I'm about to tell you is going to save you hours of beating your head against the wall using this calculator. All right, the terms on the N key, the I over Y key, and the payment key, those 3 keys. calculator is still going to make them match. Okay? And here's what I mean by that. If P&T, your payment, is happening every month, then N is the number of months. And I over Y is the monthly effective rate. And most of what we'll be looking at is either annual or monthly payments. All right, so it's usually in years or months, but it's possible to do this in days, in bi-weekly periods, quarters, whatever. And where you're usually going to fail to make the adjustment is in I over Y. You'd be tempted to put in either an effective annual rate or an APR on there when there's monthly payments. Right, so I over Y is the one you're always going to be worried about adjusting. If you've used these calculators before, there's a way to set your payments per year, so you don't have to adjust I over Y. That introduces way more problems than it solves. So we're not going to keep that. So if you don't know what I'm talking about, then don't worry about it. If you do, just know that I'm going to keep P over Y set to 1. That's the way we're going to use the calculator. Okay. Let's get some practice using this thing. Let's look at number 7 from chapter 5 onward. So actually, for the sake of being able to look back and see the same numbers, since we're learning how to use a new tool, let me pull up the example problem so we're all looking at the same ones. Okay, so number 5 says, suppose Capital One is advertising a 6.25% APR motorcycle loan. If you need to borrow $10,000 to purchase your dream Harley Davidson, what will be your monthly payment? And it gives you a note, be careful not around intermediate steps. They're less than 6 decimal places. So if you're using the formulas, you want to use stored values, but we're going to use the time value keys and let this thing do some legwork for us. They start out mapping the timeline for us, but they flip it. I'm going to do that every once in a while. That's always where we want to start with time value money problems, because especially if we're going to use the time value keys in the calculator, we've got to be really careful with the timing, and we're also going to have to be careful with the direction of cash flows. All right, so at time period 0, we're going to use the example problems method, and we're going to work it from the perspective of Capital One, the lender. From Capital One's perspective, at time period 0, they have a $10,000 cash outflow. They're paying you, or the car dealership, $10,000, the Harley dealership. In exchange for that, you're going to promise to make some monthly payments we're going to call C. Right? And you are going to do that for 60 total months. All right, this is an amortizing loan, so when you make that last payment, you pay off the last bit of interest and principal, and so the balance on the loan is going to go down to 0 on that 60th payment. All right, so the loan balance will be 0 with that last payment. And we know the APR is 6.25%. All what sort of cash flow structure do we have here? Is it a perpetuity or annuity?
Annuity.
It's an annuity, right? It's a level cash flow happening at equal intervals that ends. So this is an annuity. We could use, and I'm sure they do in the example problem here, we could use the present value of an annuity formula and solve for C, the payment, right? That'll work just fine. You've got a lot of tiny numbers in there, raised decimals, so be really careful storing your values. Or let's check out this cool tool that we have now. All right, when I use the calculator, I treat it as if I'm using the formulas. I'm going to write everything down, all of my inputs, so that inevitably when I mess a problem up, I can go back and check my work and know what's where. Right, I'd go ahead and write down the keys from left to right in the same order every single time. I've gotten habit of writing them vertically early on. There's no magic to that. Write them horizontally, do whatever you want. But I get in the habit of writing them in the same order every single time so you don't accidentally miss one. Okay, N is the total number of periods or the number of payments if you've got an annuity, which this is. So in this case, N is going to be 60. Our I over Y, remember the terms in I over Y are going to match the terms on N. N is in months, so the I over Y has to be the monthly effective rate on this loan. Right? So I'm not plugging in APR. What I need to plug in is R, right? Which is the APR divided by the number of compounding periods. And this loan, the APR, 6.25%, and the number of compounding periods are 12. Here's one of the first wrinkles with this calculator that if I can ever meet the person that programmed it, I'm going to punch him in the face. Because it causes so much frustration. And I don't care if it was a kid or someone who wears glasses, I'm getting him in the face. If they're bigger than me, I'll take the butt kick. I don't care. They're getting hit. All right, when we plug in I over Y, up until now we've been plugging in decimals like this into the formula. And if you're going to use the formulas that work out with algebra, you still need to use the decimal version. But your calculator is smart. I over Y is expecting a percentage, so when you plug it in, you're going to plug in the percentage. So when you go to use this formula now, the effective interest rate, you're actually going to type in 6.25 divided by 12 so that you get the percentage back. So 6.25 divided by 12 equals, okay, so that tells me 0.5208, and that's percent, right, which is what the calculator's going to want. Okay, present value is what's happening up front at time period 0. We're working this from the bank's perspective. And your your calculator needs to know the direction of your cash flow. So when the cash outflows are going to have a negative sign, and your cash inflows are going to carry a positive sign. If you mix those up on some problems, they can get you the wrong answer or cause an error. Right, so we're working this from the bank's perspective. It's going to be a $10,000 cash outflow. Payment is what we're looking for, so I'm going to stick a question mark there to know that I didn't forget about it. That's the one I'm solving for. And then future value, what's happening at the end of that timeline is after that last payment, balance is 0. There's no additional cash flow going on there. Okay, putting these values into the calculator. Your time value keys are a memory function. That is, whatever problem you worked last when you had this calculator out, it's still there. It's recorded. Right, so when I work the time value problems, the first thing I do every single time is clear out the memory. Because if I forget to do that and I forget to overwrite one of the keys, it's messing my problem up and I won't know it. Except that I'm getting the answer wrong. I won't be sure why. All right, clear out the time value keys. What I want to do is hit the second key, which is right above the N. And then clear TBM, which is right above the future value key. So second Alright, now putting these in, you actually put them in backwards. When you press one of the time value keys, it records whatever is on the screen. So if I want to type in 60 for n, what I'm actually going to type in first is 60. So I'll type in 60 and have it on the screen, and then press the n key. Alright, and then n comes up as n equals 60. You get however many decimal places the calculator set to, a little sideways triangle to score it out. Yeah, up here at the top. Okay. How clear that is on that screen. Okay, I don't have to clear out of that. I don't have to do anything else. I can just leave that up there. When I want to go to I over y, what I'm going to do now is, instead of reusing this 4 decimal approximation, if I didn't store it, I'm going to go ahead and type it in right here. 6.25 divided by 12 equals, and so the 13 decimal version is stored in my calculator right now, and I press the I over y key, it stores the full 13 decimal version instead of my 4 decimal approximation if I just type it in. If you don't do that, your answers are going to be off by a little bit every time. Sometimes it'll fall within the margin of error of the problem. Sometimes it won't. So default to not rounding at all. 6.25 divided by 12 equals, and then press I over y. Okay, for present value, I'm going to type in the 10,000 plus minus key to make it negative, and then press the PV key. Okay, payment is what I'm looking for, so I'm going to skip over that guy, and I'm going to type in 0, and then future value to store that. Your calculator has all those cool formulas of an annuity inside of it, so it can do all the legwork for you. Once I've got all of those in there, I can hit the compute key, which is CPT up on the top left here. And then touch the key that I wanted to solve for. In this case, I'm looking for payment. We'll come up with payment equals 194.4. This is the number they're getting used for. Alright, so what's inevitably going to happen? Inevitably going to happen when you start using this calculator is you'll type in, start working the problem, you'll use 60n. Don't ever just type this in, but for the sake of argument. Alright, 0.5208, you're going to press I over y, and then you're going to go, oh wait, what did I put on the n key? And you're going to reach back and press the n key. When you do that, whatever's on the calculator screen is going to now be stored on the n key, right? So you just changed the value on the n key when you did that. And so that's not the way to go back and look at them. Let's put 60 back on n. If you want to go back and look at what's on one of those keys because you're not sure if you got it in right, you can use the recall button just like any of the other memory functions. So recall RCL n will show you what's on the n key. Recall I over y will show you what's on the I over y key. Recall PV, etc. Right, so if you mess up and got 4 of the 5 keys stored on there, or 3 of the 5, I guess, you can just recall each one of them and look at it. If you mess one of them up, just change that one. You don't have to turn around and start all over. Alright, is that one coming out okay? Good? How many of you guys were already using the calculator without me showing you? I wasted most everybody's time. work number 10. Did anyone already try this one yet? What about this one?
Because I think it's up there.
Yeah, that was number 5.
Yes, I did.
Now, the last one, I think,
Oh, wait, not number 10. That one's not quite there. Let's see. Oh, sorry, the last one we were
it's 7.
number 7. Okay. Check mark. We're gonna work number 11, not number 10. Sorry. Number 10 is the simpler version. Yeah. Okay, that's enough going on with this one. We're going to pull up the example problem, so we've all got the same numbers. Five sessions. Okay, number 11 says you have just sold your house for $1,050,000 in cash. Your mortgage was originally a 30-year mortgage with monthly payments and an initial balance of $850,000. The mortgage is currently exactly 18 and a half years old, and you just made a payment. If the interest rate on the mortgage is 6.5% APR, how much cash do you have from the sale once you pay off the mortgage? Which you know, careful not around and you enter intermediate steps to less than 6 decimal places. Rounding around any less than 13. You won't under that problem. Okay, oh my gosh, what else going on here? What we want to eventually know is how much cash will we have from the sale once we pay off the mortgage. So let's map out everything that we know. All right, we're going to start by mapping out the original mortgage and then look at the place on this timeline we are now and what cash flows are happening. Mortgage is 18 and a half years old. Just made a payment. So let's break all the way out to 18 and a half years. I'm making monthly payments, so my N, the number of periods I'm going to use, are in months. How many months is 18 and a half years? Okay, so we're at right now month 222. And the way we figured that out was 18 months. 18 years by 12 months per year, and then plus the additional 6 months, because we're 18 and a half years in. This one's at 0.5, so it just happens that you can do 18.5 times 12, but that's technically not quite correct. But it's okay. All right, so this is where we're at right now. The original mortgage, though, had 360 payments in it. All right, and that's because we were making, it was a 30-year mortgage, and we were making 12 payments per year. So there were 360 total payments in this thing. It tells us the initial balance on the mortgage was $850,000. So if we're looking at this from the lender's perspective, and they gave out $150,000, and they expected to receive some payment C for 360 months. And had that happened, when we made that last payment, we would have run the loan balance down to 0. But that's not what actually happened, right? What happened is we're at month 222 right here. We just submitted that payment, and we just sold the house. We received $1,057,000 in cash from the sale of the house. which is great, but now we sold the house, we have to pay off the mortgage and satisfy the bank, and we get to keep what's left if there is anything left. All right, so the question is, how much did we still owe on mortgage? Do you have any ideas how we can figure that out? Besides calling the bank, right? How's the bank gonna figure out when you call them?
There's 138 payments left.
Okay. So that intuition's dead on. If we were going to satisfy the mortgage contract we took out, we still owe the bank 138 payments. Right? What we don't have to do, though, is take that 138 payments times the monthly payment and cut a check for that. Because there's interest attached to this loan. When we pay it off early, that's interest we don't have to pay. Time value is working for us in this case. And the bank doesn't care because they're going to take your repayment, turn around and reinvest it in something else. Right? So they're going to earn that interest rate somewhere else. They want the present value of the remaining payments. Okay. So actually, let's say this. The balance on a loan at any point in time is the present value of the remaining payments. Okay, so we need to get the loan balance to figure out how much I owe the bank. That's the present value of the remaining payments, but I don't know the payments yet, right? So step one in this problem then is to find the payment on the original loan. Which of course we're going to have to find the monthly interest rate and calculate. Okay, that guy's an annuity. I have the present value, I have the future value, I have the number of payments, I have the interest rate, right? It told me the APR in the problem, 6.5%. So I can use the present value of an annuity formula and solve for the payment, or I can use the calculator, since I know how to use that guy now, and let it do some of the legwork for me. And remember, we're looking for the payment on the original loan now. So N is the number of payments on the original loan. That was going to be 360 total payments. My I over Y is the monthly effective rate, so I need to take that APR of 6.5% and divide it by 12, whatever that comes out to be. Present value is what I originally borrowed. We're working from the bank's perspective, so that's a cash outflow, a negative $850,000. Payment's what I'm looking for. Value would have been 0 had we kept the original mortgage. So we go to type this in. The first thing I'm going to do is clear my time value of money keys by hitting second clear TVM. So I clear out the previous problem. And just start working left to right. So 360 and N. Store that guy. Do the interest rate. I'm going to type it in and let the calculator do the division. 6.5 divided by 12. and press equals, and it's showing me 4 decimal places, because that's what I have my calculator set to, but remember it's worked out to 13. So while it's on the screen, I'm going to press the I over Y key, for that 13 decimal version. Then type in the original loan balance, negative 850, press PV, zero's future value. Once I've got 4 of the 5 put in there, I can hit compute. Payment, in this case, is what I'm looking for. And that wonderful house has been costing you $5,372.58 per month for the last 18 and a half years. Big house. Or it's in California. So we already know we're going to use this payment to find the present value of the remaining payments, right? So we're still in an intermediate step. We do not want to introduce a rounding error here. I'm going to reuse what's on the payment key, but just in case I mess up and accidentally overwrite it, so I don't have to type it all in again, I'm going to hit store 1 and also store that number on the 1 key. And that's a just in case thing. I shouldn't have to use that, but if I do, I'll have to type it all in. Okay, so I've got the payment on the original mortgage. Now what I want to do is look at what's left. We want to find the balance on the loan, which is the present value of the remaining payments. So I'm going to take this chunk of the timeline right here and pull out and look at it separately. All right, so month 222 to month 360. Right, so month 222 is now where we're at today, right? We just made that payment, so it was month 222. Then 1 month later would have been month 223. We're on out to 360. On the original loan, but that's 138 months from now. And the way we're getting that 138 is by taking the original 360 payments we promised to make and subtracting the 222 that we've already made. So there's 138 payments remaining. Okay, so what I'm looking for now is what is the present value of the remaining payments? We've already made payment for month 222. But we have 138 payments left of $5,372.58. That should have happened. From the bank's perspective, they don't care if you pay, if you make those payments over the next 138 months, or if you just give them the present value of those payments in today's dollars, right? From our work in Chapter 3 and Chapter 4, we know that those things are equivalent. They're no different. They're just adjusted for the time period the dollars are happening in. All right, so once again, we've got annuity. We can use the present value of the annuity formula. It'll work great. Just be very careful of rounding errors. Or we can use the time value keys. And we've already got some of these stored, so this will go even faster. All right, remember those guys are a memory function? What I'm not going to do this time is clear out the time value keys. I'm going to keep some of those values in there. The interest rate's still the same. The payment is still the same. Future value is still the same. The only thing that's changing is n. Whoops, it's going to be 138. Now I'm looking for present value. Put a question mark there. move over to my calculator, I'm just going to type in 138 and press enter. And then I'm going to hit recall and look at those other buttons just to make sure nothing has cleared out on me. Alright, so recall I over Y, still good. Recall present value, we're going to ask it to solve for this, so it's going to overwrite the value that's there now. No problem for something in there. Recall payment, that guy's still there. Good. Recall future value, that's what it's supposed to be. Alright, so now I can hit compute PV present value. Alright, and I'm going to come up with a negative 521,217. I'm going to store that on the 2 key. This is what a positive version of it on 2 key. So about that second. Alright, let's put everything on the timeline to make sure we know what we've just done here. So we found the present value of 521,217.63. Came out as a negative because the way we put stuff into the calculator. And what we just found was the balance on the mortgage at the time we sold the house. So if we go back up to our original timeline here, that cash flow is happening at the same time as when we sold the house. And we received $1,050,000. But we're going to have to turn around and pay the bank $512,000 because we still owe them that much. Okay, let's talk about this negative for just a second. This happened to work out convenient for us because that's the operation we're going to use anyway. But be careful how you interpret that negative. All the calculator is telling you is the direction of the cash flow. The negative doesn't carry the sign of negative or positive in the way we're used to thinking of it. And what the calculator just told us is if we put the payment in positive, so recall payment was a positive 5,372 and change. We asked the calculator to solve for present value. So what it told us is if you expect to receive 138 payments of $5,372 and you expect to earn a 6.25% APR, then you can have a cash outflow of $521,000 and change today and earn that rate of return. That's what it's done. It's just showing you the direction of the cash flow to satisfy the other parameters. So don't interpret this as a negative, I've got to carry that minus sign around. It's just telling you the direction of the cash flow to satisfy everything else you put in. Okay, we're not quite done yet. We've got one more tiny step. The actual answer we were trying to pay off, trying to figure out is how much cash will you have from the sale once you pay off the mortgage. All right, that's easy to answer now that we've figured everything out. We received $1,050,000. We have to pay the bank $521,000. Okay, so we just subtract the 512 from the $1,050,000. Right, so the final step is to take the proceeds from sale. Someone paid us $1,050,000, but we had to turn around and pay the bank. Thank you. $6.3 roughly, and on this final step, it's okay to go ahead and start rounding. I'm OCD on that, so I tend to not do. Alright, so we get to pocket a grand total of $528,782.37 to turn around using a down payment on our next ridiculous house.
That's supposed to be total.
Sorry?
Yeah, the answer's right.
The answer's right, yeah. I just
That was backwards.
Y'all excited about exam 1 yet? I've deliberately shown you the hardest problem in the entire chapter, right? This is as bad as it gets right here. And this is one of those that once you've worked it, about the third or fourth or maybe fifth time, you'll start going to that. Right? But that's the kind of repetition it takes to get into it, and probably on about the 10th time through, you won't have to think about it that much anymore. Right? You'll read the questions and you go, oh yeah, that's that three-stepper. I need to find the payment, I need to find the present value of the remaining payments, and I just subtract that from what I got. And it'll be a very simple problem, but it ain't gonna happen without working it over and over again. Right? That's how you get there. That's how you know what formulas to use, what keys to throw out, how you should calculate it. Right, but it's definitely as bad as it gets in chapter 5. So just out of curiosity, did you guys pick up on the fact that you borrowed $850,000, you've been paying for 18 and a half years, and you still owe $521,000?
Yeah.
Yeah. You want to know how much you would have? Yeah. You want to know how much you would have paid in total if you paid all 360 payments? So our monthly payment was $5,372. Let's just times that by 360. Your $850,000 mortgage is almost $2 million.
Yeah, if you just pay like 2 extra payments a year, you can knock out so much of your interest.
Okay. Yeah, when you're on the borrowing side, compound interest sucks. Right? When you're on the investing side, okay, I'm trying to work this. Get the other side. I'm still getting that too. Student loans suck. Okay, you guys have any questions on this problem? Okay. There's other stuff in chapter 5. I wanted to talk briefly about the real rate and interest rate, but the problems are so doggone simple that I'll probably just bore you to death and mostly waste your time looking at them. What are you guys struggling with? What problems do you want to look at?
For 18 on chapter 4.
18 on chapter 4. 18 through 20 on chapter 4.
18 and 20. 18 and 20.
Alright, let's start at 18. That's the one I think it is. I've got really good news for you guys. You're going to have to do it, but it's not as hard as public. Do you guys check in the discussion board? On my finance lab. Yeah, on my finance lab. That's definitely worth checking out. There's at least one person in the online class that's asking questions. Okay, let's look at the example problem first. Let me talk about what they're doing, and let's talk about a different way to work this problem. Okay, so here's the setup for number 18. It says you're saving for retirement. To live comfortably, you decide you will need to save $5 million by the time you're 65. Today is your 19th birthday, and you decide starting today and continuing on every birthday up to and including your 65th birthday that you put the same amount into a savings account. If the interest rate is 6.5%, how much must you set aside each year? Make sure that you have $5 million on your 65th birthday. All right, so they map out the timeline for us. Today's your 19th birthday, so we're treating that as time period 0. We're going to go out to your 65th birthday, which is 46 years from now, and we're making payments at every point on that timeline. We want to end up with $5 million. Okay, that introduces a real problem for us because either the present value or future value of an annuity assumes you've got an ordinary annuity with payments happening at the end of the period, or an annuity 2 with payments happening at the beginning of the period. With either one of those, you need an empty space. With an ordinary annuity, this time period 0 needs to be blank, no payment happening there, right? That's got to be your present value spot. And then you can have a payment on the end. With annuity 2, you need a blank space on the end, no payment happening here. That's not what's happening with this. All right, so what the example problem does is set up the present value of an ordinary annuity right here, and then they just lock an extra payment on it, right? So this plus C right here is plus this payment at time period 0. Okay, this is the present value of an annuity formula, so it's bringing all these things back to time period 0, and this payment is already in time period $0. So we just add on. Right, that's where that plus C is coming from. No, that's not a formula on your formula sheets. If you have to make that adjustment, you'll just have to know to do that. Alright, so I'm just going to explain what they're doing, and then we're going to look at a much simpler way. Alright, so they use the present value of annuity formula. Notice here that the N is 46. There are 46 payments in this annuity, right? Plus the 47, but that one's already in time period $0. We don't need to discount it, so it just gets added on to the end right here. And we know the present value of the annuity, so we're going to take that $5 million we want to end up with and put it in present value terms, and then lump it into that formula right here, and then solve for the C that makes it true. Right? Is that the plus one
Yes.
you're talking about? Okay.
Why is it not plus a payment instead of plus 1?
Right, because they factor that out. That C is over here. Yeah, that's where the plus one is coming from. They solve this formula right here for C. And this C right here becomes just a plus 1 to factor it out.
So my question is, will this problem be on the test?
You have a valid of between a 30 and 50% chance of seeing it on your test. If you take the test 3 times, yeah, you're gonna get it. You're gonna like what I'm gonna show you. Okay, relax.
I worked at 5 and still didn't get it. I gave up.
Okay, the last step is where things get really funky. If you're using a financial calculator to solve for payment, what they do is turn this thing into an annuity due with 47 total payments, right? You got to set your calculator in begin mode. I never recommend you do unless you absolutely have to, because if you forget to take it out, it screws up every time you work on that. So let's forget what the example is all do. Check this out. Let's map out the cash flows that are actually happening and see if there's a better way to do it. Alright, so our 19th birthday, we're going to start saving today. We're going to save up to our 65th birthday. Alright, so I'm going to leave a little space to the left of my 19th. I'm going to back my timeline up one period in just a second. Alright, so we're going to go out to 65, and that would be 46 total payments. Alright, I want to make some payment C into my account, and I want to end up with $5 million. Okay, we have to jump through all those hoops and go through all those steps because we don't have an ordinary annuity. Can we make this an ordinary annuity?
Clearly the answer is yes.
Yes, it is. How do I do it? If I take one of the payments off, but I can't just delete a payment, what's another way I can do this? Yeah, what if I back this timeline up like this? What if I go back to my 18th birthday, right here, turn my 19th birthday into the first period, 20th birthday into the second period, 21 into the third period, and my 65th becomes 47. Somebody read the discussion board. Or do you over that? Yes, that's so awesome. Hey, I've worked this problem for 2 years, going through the complicated way, and a student just said, "What if we just backed it up one year?" I'm like, you can't do it. Whoa, that's awesome. Okay, so look what we have now. We've got an ordinary annuity. So if I make this my present value, right? What happened on my 18th birthday? It's already passed, right? Did I make a payment? No. Did I have a present value in my account? No. So now I have a time period 0 that has a 0 cash flow. And my first payment happens 1 year later, 1 period later. My last payment, my 47th payment, occurs when I want to end up with a $5 million. So now I've got an ordinary annuity, right, with a present value of 0. So now I just need a payment off of that. So I can use the present value of the annuity formula or the future value of the annuity formula. Either one will work fine and solve for payment, or now we know how to use this thing. Let's plug in the four we know and ask it to solve for the fifth. And the total number of payments is 47. Our interest rate is 6.5%. This one's in years, no adjustment needed. Present value is 0. Payment's what I'm looking for, and I want to end up with $5 million. Alright, so clear out my time value keys from the previous problem, and put everything in. 47 is in. 5 out of Y. 5 million future value. And you're done. So just to reiterate, that's coming out as a negative because I wanted a future value. I put that in the positive payment. So if I want to receive $5 million, it's really 46 years from now, but it's 47 total payments from now, then I need to today have a cash outflow of $17,000 change in my bank account to make that happen. So it's just telling me the direction of the cash flow, but it's a $17,000 payment change, which I assume is what they're coming with. Yeah. What you're going to run into in this class over and over and over and over again as the problems start to become more complex is that there are almost an infinite variation. There are almost infinite variations of ways to solve the problem, right? And they're all, as long as you're following those rules, right? The 3 rules of time value problems. Only compare and combine values happening in the same time period. Compound if you're going forward, discount if you're going back. However you work it perfectly fine, right? What the example problem is fine. It's just unnecessarily complicated. Right, so work it whatever way makes sense for you, but I urge you to simplify wherever possible. Reduce the number of steps. Right? If you see a way to simplify it that makes sense for you, go for it. Do it. Any questions on this? Okay, what did you guys do? Another one out from chapter 4. Which one was it? 20. Yeah, this was fun too. I don't really have a shortcut for you for this.
I didn't have 18 or 20 on my computer.
Alright, so you just turned 22 years old, received your bachelor's degree, and accepted your first job. Congratulations. Now you must decide how much money to put into your retirement plan. The plan works as follows. Every dollar in the plan earns 6% per year. You cannot make withdrawals until you retire on your 65th birthday. After that, you can make withdrawals as you see fit. You decide that you plan to live to 100 and work until you turn 65. You estimate to live comfortably in retirement will need $135,000 per year, starting at the end of the first year of retirement and ending on your 100th birthday. You contribute the same amount of the plan at the end of every year that you work. How much do you need to contribute each year for retirement? All right, they were kind enough to draw out the timeline for us. Let's do our own here instead of flip it again. I don't know why they insist on doing that for a while. All right, so today, right now, is our 22nd birthday, right? the same amount of plan at the end of every year that you work. So mercifully, we're going to start making payments into this thing one period from now, not right now. Okay, and we're going to do that up to age 65, right, which is 43 years from now. We're going to make 43 total deposits into this thing. And then we're going to start making withdrawals on our 66th birthday. We're going to run that out to age 100. Start receiving $135,000 per year. Okay, so I know what I want to be able to withdraw after I turn 65, but I need to figure out how much I need to deposit to make that happen. I'm going to start with this one. I'll find that, say that again, I think you're right.
Present value at 43.
Okay, present value 43 years from now, present value of what? Yeah, we're going to find, remember the same idea applies, like the present value, or the balance on a loan at any point in time is the present value of the remaining payments. Well, if I want to know how much cash I need to have in the bank at age 65, right, because I'm done working at that point, I'm done generating income, I want to live off of what I've got. So there's some lump sum I need to have in the bank at age 65 that will allow me to withdraw $135,000 until I will turn 100. And so what I need is the present value of that retirement annuity for us. So step one, find how much cash you need in the bank. At age 65 to fund your retirement. And another way of stating that in finance terms is the present value of the retirement annuity. The way the problem presented is timing of the cash flows. We've got an ordinary annuity. We can use the present value of the annuity formula, or we can use this cool new tool we picked up. Let it do some of the legwork for us. What's the number of payments? What's my N on the retirement annuity? How'd you figure that out? Alright, so my last one's occurring at age 100. My first one is occurring at age 66. Total number of payments in the retirement annuity.
That's gonna be 100 minus 14.
It's 100 minus what? How'd you know to do 100 minus 65?
Because that's whenever you start getting like your payments, like at 66. So you do much less.
So 35.
It's 35 total payments. All right. Now here's what introduces a ton of confusion and why I wanted to camp out there for a second. Your first payment's at age 66, so you're going to be tempted to do 100 minus 66, or at least I am. Right? If you count those up, like if you have to do what I do, draw a picture and count up on your fingers, though, do 66. That's actually payment number 1, right? Not 0. So 66, 67, 68, 69, 70, all the way up to 100, you're gonna run out of fingers and toes, right? But double back, you're gonna come up with 35 total payments. All right, so if you're doing the subtraction on the timeline, make sure your endpoint is year 0, not year 1.
So why you put 35 instead of 43?
Right now you're figuring out the retirement annuity.
Yeah, good question, and yes, that's exactly right. Right now, what we're finding is the present value of these animals. Right, so this actually is year 0, this is year 1, year 2, and 35. Okay, so step 1 is we're using the back end of the timeline, I mean the present value of those payments we want to generate. That's the 35 total payments at 6% per year. Present value is what we're looking for. The payment we want to collect is $135,000. And the future value in this is going to be 0. We want to collect income until we turn 100. Right? So the idea is we take that last $135,000 payment and we pray to God we don't live to 101. Right? So we want to run out of money and bread at the same time. So the future value on that account is going to be 0. The once we draw out that last payment. All right, so second clear TDN, get rid of all that stuff. Present value. All right. I entered the payment as a positive, so I'm going to come up with a negative present value. It doesn't much matter which way you go on this one. All right, and this is an intermediate step. I'm going to use this to now figure out how much I need to pay into my account to end up with it. So I'm going to store this value on the 1 key, just in case I accidentally overwrite it to something. All right, so what I have just found is that I need to end up with, at age 65, when I make that last payment, I need $1,957,000, $1,957,263 and roughly 26 cents in the bank. All right, that's what I need at age 65. I think $135,000 a year sounds like a lot. Consider that there's no adjustment in inflation for this, and just imagine what the cost of health care in your elderly years is going to be 40 years from now. All right, so on our 65th birthday, we want to end up with just shy of $2 million in the bank. The next question we need to answer is, what payments do I need to make to add up to that? All right, so that's the future value of an annuity, and I need to solve for the payment that makes that thing true. But I know everything else. I know the number of payments. I'm going to make 43 total payments in this thing. I know the interest rate. I'm earning 6% per year. I know the future value, just under $2 million. I know I'm starting at 0. So I need to find the amounts you need to contribute each year to fund your retirement annuity. All right, and you are exactly right. Just an annuity again, so I can use the future value or affiliation present value annuity formula, either one work, or I can use this calculator again. Where things are going to shift around a little bit on me now because I'm moving on the timeline. Okay, I've jumped back to today now. I figured out how much I need to have saved by age 65. Today is now my 22nd birthday, and I'm starting with nothing. What I need to do is find the payment C that adds up to $1,957,000 and change. All right, so I'm going to make 43 total payments. Each of those payments are going to earn 6%. Present value is 0. I'm starting with nothing. Payment is what I'm solving for, and the future value, what I want to end up with, is that